Hi, welcome to the Signal Path. Today we're going to review the Rigol 3068 Digital Multimeter. This is a 6.5 digit bench multimeter that's sitting right behind me. You've seen me use it in some of the previous videos. Today we're going to look at it in some more detail, some of its functionalities. We'll take it to the limits of its performance so you can become familiar with what this multimeter can do. But I don't want to just show you the ins and outs of the menus. I'm sure you can do that yourself. What we want to do is to set up some simple experiments, and then we will use the multimeter to do some measurements. And at the same time, you get an idea of how easy it is to use this multimeter and to get it to do what you want. So first we'll do some physical look at the multimeter, see how it looks physically and where the buttons are and how good it is to access the different menus, and then we'll do some simple experiments. So let's get started. So here I have the Rigol DM3068 right next to an Agilent 34401A. Both of these are 6.5 digit bench multimeters. The reason I'm comparing it to the Agilent one, even though this is somewhat of an older model, is that they cost about the same. You can find an Agilent meter like this online, and they can go, depending on the condition, they can be up to $800–900, which is kind of the cost of this one. Rigol also makes a lower cost version of this, a DM3058, which is a 5.5 digit meter with pretty much all the same capabilities. If you look at the front, the layout of the input connectors is exactly the same. They all have the low current, the 4-wire resistor, the voltage, and the high current settings all laid up in exactly the same way. Agilent has this power switch that allows you to go in the front and the back of the instrument to measure it. This guy has only inputs that are in the front of the instrument. So if you put this on a rack somewhere, then you can connect it from the back, so you don't have to plug it in and out. Both of them have the power switch on the left. This guy is a soft power on with a hard power on button at the back. Now, in terms of display, the Agilent uses a vacuum fluorescent display in order to display all of its measurements. Now, VFDs have a very high contrast ratio, so it's really easy to see in the dark. Now, Rigol has opted for an LCD, which is the dot matrix, so it's a fully configurable LCD. You can show anything you want on it, and it has this bluish white backlight color that makes it quite easy to see in the dark or in the light. So really, there's not much sacrifice by using the LCD, but at the same time you get all the configuration that you can display anything you want. In fact, they have all these soft buttons at the bottom, and depending on which menu you're in and where you are in your settings, you can select a particular function with these soft buttons. As for the main function, Rigol has a backlight on every one of these buttons. So all the front panel buttons except these directional selectors have a backlight, so you know right away which setting you're on. If you press the ohm button, the ohm will light up and are all green. So you can quickly tell what function you're using, whereas the Agilent, you have to kind of look at the display and make sure that you're in the right setting. As for some of the other buttons, you have trigger, utility, math functions, and measurements. Tons of built-in functions into this instrument, as well as a run, hold, single, which is easily accessible, which behaves kind of like an oscilloscope. You can trigger the measurement, you can have it continuously running, or do a single measurement at a time. In the front panel of the Rigol, there is a USB port, and this USB port allows you to input configurations into the unit or get your data that you've saved on the internal memory right off the instrument. Or if you have multiple units, you can save the settings of this unit onto the USB, plug it into another machine, and then you can replicate your settings if you are doing some kind of an array measurement. So there's a lot of functionality that you can get out of using the front panel USB to get the data in and out very easily without having to connect it directly to the computer. Now if I were to turn this back, both of these units offer some connectivity to the outside world. So if you look at the Rigol unit, the Rigol unit, as all the Rigol instruments that I have seen, they all have RS-232, USB, Ethernet, and GPIB connectivity standard built into them. This is a huge advantage. Not only is it legacy backward compatible, so if you're using old equipment, you can just array them in a GPIB or RS-232, but having a LAN and a USB connection opens up a whole bunch of other possibilities. For example, with a LAN, you can have a built-in, kind of like a web server into here where you can log into the instrument directly and use this built-in functions in a browser to check its configuration or get measurements which this instrument supports. Also, if you're using the LAN to communicate with this, the LAN cable can be 100 foot long, so you can put this quite far away or connect it to a hub and access it through the internet. With a USB, it's a plug and play. If you have the right drivers, you just plug it into your computer and then you can talk to it in the same way with the same SCPI language, and we will see that in one of the demos. This older Agilent model only supports GPIB and RS-232, but this ease of connectivity of all the Rigol instruments has been a huge advantage for me when I've been trying to get data in and out or communicate with these things. So what I'm going to do now is I'm going to put these back, and then we're going to turn them on, and I'm going to compare the measurements I get from this guy with the Agilent one or with some other instruments I have. So let's go through all the fun things. The instrument is shipped with a power cable and a USB cable, which I've already connected to the unit, and it comes with these probes that have very nice soft cables that you can these guys are going to last for quite some time. They're all rated for category 3. These are 1000 volt cables, 16 amps rated, and they have these nice plastic covers on the inside to protect you from accidentally touching them if the other end is connected to something high voltage or hazardous currents. So they also ship with these little alligator clips, and these little alligator clips screw on right at the tip of these guys because there is a little screw position here, and you can kind of connect these in here, and then they turn into little alligator clips so you can connect them to wires. The tips are very nice, very sharp. The probes feel very good in hand, and they're very sturdy. I've been using them, since I got this quite a while ago, and I have had no problem with them. Very happy with the feel of these cables. It also comes with a manual, the quick ride manual, a bunch of extra fuses, and of course the calibration certificate that tells you that your unit is calibrated to a particular standard. So let's power on the unit, and let's take a look and see what it does. So here it is. It's where it's always been sitting. So I'm going to power it on. One thing I wanted to point out is that the power on sequence is a little bit long. It takes a bit of time for it to actually start up. I think it's going through some internal calibration, and it goes through self-checks. I think there are ways to make it a bit shorter. They may do that with future firmwares, but once it does start up, then no problems. So it starts up pretty much like all multimeters in the market in the voltage configuration. So you can see, as I told you before, that whatever you press lights up. So here if I press the current, now you have current light up, and it displays nice, very high contrast. I can see it. It has very nice viewing angle. From anywhere I can read these quite easily, and it has a bunch of soft functions at the bottom that you can select. You may not be able to see it so well on the camera, but you're gonna have to take my word for it. The display is very easily readable. So it starts up on an automatically running on voltage, as I mentioned, and it has a voltage, current, ohms, the short or continuity test, frequency. It also does AC, of course, AC volts, AC currents, measures capacitance, measures diodes, and then it also measures a sensor. The sensor configuration we'll talk a little bit about. Very flexible. You can put pretty much any sensor on this unit. So let's do some simple measurements. So in order to measure the voltage and the current capability of the meter, I'm going to use the Keithley source meter that I have here. The advantage of using this unit is that it can go down to microvolts all the way up to 210 volts with great resolution. It's a little bit out of spec right now. So what I've done is that I have turned the voltage source on to 0.5 millivolt, and its internal measurement says that when I set it to 0.5 millivolt, it's actually doing 394 microvolt. At the same time, I have connected it to my Agilent meter down here, and the Agilent meter is saying 378 millivolt. So even though it's saying 0.5, 378 microvolts, so even though it says 0.5, it's really doing 0.37. So I'm going to take this and I'm going to connect it to the Rigol, see if you read the same value that is displayed here. So we're looking for something around 370 microvolt to show very low voltage accuracy. Here we go. And 375 microvolt, almost exactly what the Agilent meter is saying. So I can go up by 1 millivolt at a time and see if this guy can follow. So I'm going back to the Keithley meter and I'm going to change it by 1 millivolt up. There we go, 1.375, almost perfect. Another millivolt, 2.375. So it's doing absolutely perfectly. It's fully calibrated as it should be. But you can see that even though the Keithley is not in calibration, but its resolution is still there, and you can do the proper steps of voltage. Now one other thing I can do is I can go to the other extreme and try out the really high voltage measurement. So I'm going to plug this back in here. So we're going to go from millivolt range all the way to hundreds of volts. So change the range up, all the way up, 100, 210 volts. There it is. So now I'm at the maximum voltage this instrument can do. So now you got to be a little bit more careful if you do this, because this is going to give you a nasty shock if you touch it, and it's DC, which is even more dangerous. So here now it's the internal measurement says that it's 209 volts 0.995, and my agitometer is saying 209.9976. So again, very close. So I'm going to disable this output this time, because I'm going to disconnect this. I don't want to accidentally touch it. Now this also allows us to see something else. I'm going to focus on the Rigol meter, so you can see the auto range speed. So right now it is automatically auto ranging, so because there is no voltage present, it is at its lowest range, so it's measuring all the way down to millivolts and microvolts. Then I'm going to turn on the acutely and see how fast it can give me the correct value. Here we go, 3, 2, 1. It took just about a second to jump all the way from microvolt measurements to hundreds of volts. So you can see it gives me 209.967.1. So it's still giving me hundreds of microvolts of measurement down there. So I can go ahead again and try and change the voltage by about 10 millivolts at a time. Going down by 10 millivolts, you can see this digit became 5, 10 millivolts, 4, no problem at all. How about by 1 millivolt at a time? 6. You go. It's a little bit not as good, but it's most likely it's actually my apologies. It's because my instrument is doing, you can only do 5 millivolts at a time in this range. So I'm going down by another 5, by another 5, another 5. So you can see it's following pretty well. So even though at its highest range, I can still measure millivolts quite accurately, no problem at all. So now let's look at some of the menus. Let me focus in a little bit more. So what options do I have here? Well, I have the auto option, which is active right now. At the top it says DC volts. There's this little thing down here that's rotating. Every time it jumps, it's done one measurement. So it tells you that it's in auto mode. This number 10 is the integration time. So this instrument allows you to change the integration time of the measurement. By doing that, you can do more measurements per second, and it can do internally thousands of measurements per second. Or you can get more resolution. Right now it's kind of a compromise, a balance between the two. So if I go to the right by pushing the directional button here, I can change that to 100. Now it takes a lot longer for it to do one measurement. You can see if you look at here, every time it moves, it does one measurement. So it's not taking a lot longer, but you have gained a lot of accuracy by doing that. I can go the other way. Let's say I can go all the way to 0.06. Now you can see it's doing measurements much faster. I can go even one more. You can see it's now returning quite a bit of measurements per second onto the display. It's doing thousands internally, but you can see we lost quite a bit of resolution here. Now we can only go down to tens of millivolts in this setting, but by going back up, of course, you can get your resolution back. So there are advantages of being able to do something like that when you're doing measurements that you want a quick readout. So we can also change the range up and down manually if you didn't want to be in auto. You can also do a relative measurement. So if I press the relative button, it zeroes the instrument. So now I can go down using the Keithley meter by, let's say, by 10 millivolt, and it should tell me minus 10 millivolt. There we go, minus 10 millivolt, almost perfectly. So it's doing a relative measurement. I can press the relative measurement again, and it goes back and gives me the absolute measurement. So that's nothing out of the ordinary. It has a hide button, and it just hides the menus at the bottom so that they don't clutter up your display. That's about that. It also has a history. So this whole time it's been doing measurements in the background, and as long as it's in run mode, so it's continuously measuring, it will have a history recorded for you with everything that you've measured, which I find extremely useful, because sometimes you're not paying attention and then you realize, oh, you know what, I wanted to know what the maximum and minimum was. It's all in the memory already. So it tells you that you're in DC volt, the range is 200 volts, you have 31 records, which you can update. As we see, it's measuring in the background continuously. So if I keep updating it, it'll just keep doing more and more measurement. And it's telling me that the maximum has been 209 volts, the minimum was 209.914, so on. The average is this, the standard deviation is that. So it has every kind of statistical measurement that you want in here, but you can also look at it in a list. So you can see all the measurements that you've done. You can also look at it in a histogram. which is very useful. We'll do a little bit of experiment with that. So you can see the histogram shows me that almost all of my values are at the average of 205 volts, which makes sense because I haven't been doing anything else. But if I go back, for example, and I'm going to change the voltage from 200, I'm going to go down to 100. So now it's doing 100 in the background. So if I go out, you see now it's 100. So then if I go into the history again and I update it a few times and I look at the list, at the very end of the list, I can go to the end. You can see it's now doing 100 at the bottom. So now if I go back up and look at the histogram, now my histogram has an average of 202. There's not enough measurements done in order for me to actually shift the histogram out, but I will be able to see it in my, I would be able to see that inside this minimum and maximum. So now the minimum value is 109 volts. And if you let it run for some time, then your histogram will spread because you have enough measurements at 100 volts in order to influence the histogram of your measurement. You can also do other things, like, for example, you can do you can look at the math function, and if you press the math function, which by the way now the math button is turned on, by pressing the math function, now you have a whole bunch of new capabilities. You can do a trend, you can look at the histogram which we were looking. Now you can see that I've been doing some measurements. Now the histogram has 2 points on it. Most of it is still 200, some of it is now 100. So if I go back and if I look at a trend, it actually plots for me as a function of time my measurement. Now the resolution here is so small, you can see the tiny changes at around 100 at 100 volts. If I were to go back to 200, all of a sudden you can see that it has a huge jump. So the line at the bottom here was 100 and the line at the top is now 200 volts. So all these math functions that are built into the unit you can access very easily, but you can also save everything. So if I were to go to the histogram, I can actually click on save, and then I can either save it on the internal memory, which they call C here, or you can have a little USB, then it will show up underneath this. You can select it and you can dump all the values directly onto the USB, no problems at all. So a lot of functionality right at your fingertip available for you to access. So let's take a look at that trend one more time. So what I'm going to do is I'm going to turn on my Rigol arbitrary waveform generator, and then let's see how it behaves. So what I want to do is I want to put a little sinusoid into the multimeter at a low frequency and see the trend function take place. So I'm connecting the USB and I'm going to the BNC, then I'm going to say this is at 1 kilohertz. Let's put it at 1 hertz. It's 5 volt peak to peak. Let's change that to 1 volt peak to peak. And I'm going to enable the output. And I'm going to change the range. And I'm going to put it into a voltage range like that. There we go. So now it's measuring as a function of time. So if I go to math and I go to trend, you will see that it is measuring as a function of time. So now the frequency is a little bit too high, so I'm going to change, go back in here, change the integration time to be a little bit faster. Here we go. I'm going to go back to the math and to the trend, and here we go. Now you can see that it is actually measuring as a function of time my sinusoid. So it's showing the trend of my voltage, and it has in this area it has a little zoomed in version of what you're looking at. So because it's changing so rapidly, it's kind of jumping all over the place. But by changing the integration time, because I changed the integration time to something faster, I went to 0.06, I can go even faster than that, and now it is measuring even faster. So for example here, if I go back to math and I go back to trend, you can see that it has no problem measuring the sinusoid. I can increase the frequency of the sinusoid by a factor of 2. I can go to 2 hertz. So now you can see that the frequency has changed, it's now changing twice as fast. So the trend function is very useful if you're doing a bunch of measurements and you want to find out if some periodic behavior, some kind of noise is present in your system. You can easily find out. So there's one other little thing that I wanted to point out. Here I'm connecting the input of the Rigol meter directly to the input of the Fluke handheld meter to measure the internal resistance of the Rigol multimeter. You can see the internal resistance is spec'd to be 10 mega ohm, and it's pretty much exactly 10 mega ohm. So now if there is some other capability built into this unit. Let's say you're doing a measurement on the multimeter that requires a very high input resistance, and 10 mega ohm is actually not enough. What you can do is you can go to utility. You can go to measure, and then under measurement function you have the integration time, which I've talked before. Then you have this resistance. If you click on that, you can either choose to be at 10 mega ohm, or you can choose to be more than 10 giga ohm. So if I click that, now the input resistance of the meter has gone up so high that the Fluke multimeter is unable to measure it. So if you're doing some very sensitive high resistance voltage measurement, you can actually change the input resistance of this guy to be at 10 giga ohms. So if I connect to the 10 giga ohm, I can go back and measure the voltage, is no problem. So the Fluke multimeter is putting out 3.8 volts in order to try and find the appropriate resistance. It's unable to assist putting its maximum voltage. Now I can go back, measurement, and I can change the resistance back down to 10 mega ohm, and I go to voltage, and now the Fluke multimeter is doing 1.834 volts, and it is again able to measure 10 mega ohm of resistance internally. So it's one little thing that you might find useful. Let's quickly look at measuring some very low currents. So here I have set the kit instrument to 1 microamp, and I'm connecting it to the Rigol meter, and the Rigol meter is reporting 995 nanoamp, no problem. We can even go lower than that. I can go to, how about 100 nanoamp? There it is. It's telling me 95, which is probably correct because that unit is out of calibration, but I'm going to measure another unit and I'll show you. So we can go even lower than that. How about measuring all the way? Now, right now I have set to 30. How about 10 nanoamp? So this guy is, so the Rigol instrument is telling me that the current is actually approximately somewhere between 6, 5, 6. It's jumping up and down, but you have an idea that if I were to go to the histogram of this, and I were to look at, I can reset this, and I go to the histogram, and I look at the mean, the average value, 6, I can update it a few times. This is one of the advantages of having this function built in. Make sure you can see it. So it's telling me that if I keep updating, 6.5 nanoamp is what I'm measuring with this instrument. And the Keithley instrument is telling me that it is about 11 microamp, which I suspect is incorrect. The Agilent instrument has no hope. It cannot even measure this amount of current anyway. So let's go to another Keithley current meter. So remember, 6.5 was the magic number. Connect this, and look at that. With the 100 nanoamp, 6.8 nanoamp is what the instrument is putting out. I believe some of it is being lost in the cable because the current is so low that the leakage through the dielectric of this BNC cable is affecting the measurement. But this number matches perfectly. This is the calibrated unit. This number matches perfectly to the Rigol, all the way down to, we're talking about measuring nanoamps at a time. This guy can measure nanoamps all the way up to 10 amps with remarkable accuracy. So I'm very happy with the current measurements in this unit. So let's measure some capacitance. I have a small capacitor like this. It says 6.8 on it, which refers to the fact that this is 68 picofarad of capacitance, a very small value. And I have a big capacitor that we can measure to show the extreme ranges of capabilities of this instrument. This particular capacitor is a 16 volt 100,000 microfarad, which is a 100 millifarad. So 0.1 farad capacitor is usually this is a computer grade power supply capacitor that's used. So let's measure these two, but in order to know what we're actually measuring, let's use first an actual LCR meter. So I'm going to use my HP LCR meter, which is quite an expensive unit. So I'm going to connect the little capacitor to it. These are the terminals. We've seen this before in some other videos. So if I were to connect it, left, positive and negative, like so, and you can see that it is reading about 70 70 picofarad, which is correct, and the Q is all over the place. But if I choose the proper frequency, you can get at 100 kilohertz, it's about 70 picofarad. So it's fairly consistent at all the measurement frequencies. So we're looking for 70. Now let's go to the Rigol meter and see if it can measure such a tiny capacitor. I tried this capacitor on all my other meters except the LCR meter. I didn't have anything that could measure this tiny capacitor. So what I've done is that I've selected the capacitance measurement. Everything is in default settings, auto range, and I'm hanging a little cable like so from the instrument. It's just kind of hanging in the air like that. Now when it's at rest, it will pose its own capacitance. The LCR meter that I showed you just before this, I calibrated it out. So what I can do is I can go here and tell the meter, right now it's reading 27 picofarad, which is the capacitance of the instrument and capacitance of the wire. So I can go click on relative. So now it's doing relative measurements, and I'm going to connect my capacitor to it like so. I'm going to try and have the cables rest in a similar location they were resting before. There you go. And I'm reading, it jumps around a little bit, but I'm reading around 60. So if I go to the history measurement, let me reset the history, and I go in here and I update it a few times. As you can see, it's already done 80 measurements. And if I go down and I look at the average of about 63 pico, which is really, really good considering that I'm just hanging this capacitor in the air and I've moved the cables already and I'm doing a relative measurement. So it's doing a very good job measuring such a tiny capacitor that I could only measure with my LCR meter otherwise. Now what about a very large capacitor? Well, let me remove this guy. Let's go back to the capacitance measurement, take the relative measurement off. So again, the probes are sitting in the air. Here I don't need to do relative measurement because the capacitance is so much larger. This is a 100 millifarad. So I'm going to connect it up. Let me have it focused here. Again, the reason I chose this capacitor is because I couldn't measure this with anything else I had. They would just simply not give me the right value. And even my LCR meter can't measure a capacitor that is this large. So I'm going to connect it up. Here's the negative terminal. And here's the positive terminal. Now, as soon as I connect it, it's going to search for the value of the capacitance. It's going to go through several orders of magnitude. Here we go. So now it's nanofarad. Now it's looking in microfarad. Now it's looking in millifarad. And finally, 100 millifarad, which is really amazing because I can't believe that this instrument can measure down to picofarad, tens of picofarad with accuracy, and it can measure all the way up to just below a farad with remarkable accuracy. I'm very, very happy with the capacitance measurement capability of this unit. So now I have the instrument set to the continuity test. Now, one nice thing this guy does is that you can tell it what you mean by continuity. You can click on set and you can say, well, anything less than 10 ohm, you're considering a short. But you can change that value. You can change it to whatever you want. So let's say you're measuring a bunch of things and you want to find out which of them is less than 100 ohms or 1 kilo ohm or 10 kilo ohm. Then you can set it up directly using this. You don't have to rely on the multimeter. You can have an audio feedback, but you can set the resistance. So I'm going to go back to the default, which is 10 ohm, and I go back and now it says it's open. I have the probes connected. So if I connect the probes, you can see that it gives me the tone, and it's very fast. You can see it's hard for me to actually do it fast enough for it to miss a beep. Now, one thing I have to point out is that this does not do a latching beep, which means that like the Agilon does, where you, as soon as it detects a touch, no matter how short that touch is, it's going to still give you about maybe half a second of beep. Now they've told me, I've discussed this with them, they've told me that they can implement that to have that behavior, which I find very, very useful because you may miss a very short tone. And it doesn't do that scratchy noise once you do that. So that is, in terms of speed, it has the speed to do that, and they will put that functionality into the firmware, which would be very useful. One other thing they can do is to do the opposite, which is to do an open test. So when there's a short, it will not beep, and as soon as there is an open, you can then define if the resistance goes above a certain value, it can start to beep. So they can implement all of those things without any issues. Let's look at measuring some AC voltages and frequencies. Here I have the arbitrary waveform generator set to 5 volt RMS. I hope you can see that. It's set to 5 volt RMS at 1 kilohertz. So if I go back to the Rigol multimeter. I have the Rigol multimeter set to measure AC voltage. You can see this is lit up here. So it's telling me 4.968, which is very close. I can change the frequency from 1 kilohertz to, let's say, 10 hertz. And right now I have the integration time to 200 hertz, which is too fast. So now I can change the integration time to, let's say, something like 20 hertz. Then it will give me the right value again. So it has its own internal integration time, so you can have it if the filter is set to slow, medium, or fast. Right now I set to medium. So let's go back to 2 and then let's go to 10 kilohertz. There it is. So 4.955 volt RMS, which is coming from the instrument at the bottom. But it has a capability of showing both the frequency and voltage at the same time. So if I press the second button and I press the frequency button, now it's giving me two measurements simultaneously. It's telling me the frequency is 10 kilohertz and the voltage is 5 volts. So I can go from 10 kilohertz, for example, to 30 kilohertz. There we go. Now we can see 30 kilohertz at 5 volts. We can also just measure frequency on its own. If I click on frequency, telling me exactly 30 kilohertz, the integration time is now 100 millisecond, so I can increase that. It's rated all the way up to 1 megahertz. Here we go. So 1 megahertz perfectly, but it works above 1 megahertz. I can go 2 megahertz, no problem. 3 megahertz. And now I can change the integration time a little bit faster. No, doesn't look like it's going to do 3 megahertz. Let's see, let me go back to 2.5 megahertz. No, doesn't like that. Oh no, it was measuring 2.5. So it can measure above what it is rated at. So you're just measuring 2.5 megahertz without any problems. So you can go above what is rated. It won't be perfect, but at 1 megahertz, no problem at all. So let's take a quick look at the diode function. So I have selected the diode, and when there is nothing connected to the terminals, it says open naturally. And now I can try with an LED to see the different voltages that this guy can detect. So this is a red, green, and blue LED, RGB LED. So if I turn it on, I'm connecting it to the red, and you can see that it says 1.770 volts. That's the junction potential at a particular fixed current. So it raises the voltage until it detects a particular current, and then it gives you the junction voltage. So it can turn on a red LED, which is nice, and I can connect it similarly to a green one. But when I connect it to the green one, it says open. And I think what it's doing is that, if I remember correctly, anything more than 2 volts, any junction more than 2 volts, it just reports as open. But this should be something that can be easily changed in the firmware, that to basically show any voltage above, let's say, anything that's less than 5 volts, it would count as a junction, because that way you can measure some kind of Zener diodes or maybe higher voltage LEDs. For example, you can even turn on the blue one, which requires the highest voltage, but it displays it as open. So that's something that I'm going to discuss with Rigol engineers to see if they can have it show the actual voltage, anything higher than 2 volts also. One of the most sophisticated and flexible functionality of this multimeter is its sensor capability. So the sensor function allows you to basically convert any type of sensor into a reading that you like. So as long as a multimeter can measure the output of a sensor, it can be voltage, current, frequency, capacitance, it doesn't matter. You can turn that into some type of an output given the relationship between the output of the sensor and whatever you're measuring. For example, the simplest type, the most common type, are thermocouples. We know that a thermocouple with a metal junction gives you voltage as a function of temperature. So you can measure the voltage in here, which is what multimeters do. They measure this voltage, and there's a relationship that describes the temperature as a function of this voltage, and then it will give you the actual value of the temperature as a result of that. So this instrument has built in many different types of thermocouples already, but you can define any kind of sensor that you want. But let's take this one, for example. So I will connect this thermocouple that I have onto the two terminals, like so. Here's one, and here's the other. And then all I need to do is to edit the existing sensor configuration. So let me go in here so you can see. So I will just go to edit, and I say that this is a temperature one because it has built-in temperature thermocouples already into it. It can be anything. So I select the type, and I know that this is a thermocouple, TC. There's other types of temperature sensors. I click on thermocouple. Now I can tell it what type it is. So I type. So it has all the types B, E, J, K, and all the different types of thermocouples that are in the market. I happen to know that this particular one, this is a type K thermocouple. So, and I select that, and I go back up, 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 and I say done, and I say apply, and there it is. It gives me 27 degrees, which is the temperature that is right now in my room. And I can also tell it to show, if I click on display, I can say all. So now it's showing me not only the measurement it's getting from the thermocouple, but it also is telling me what that corresponds into temperature. So it's easier to see here. I could have a different type of sensor that, let's say, outputs frequency as a function of light. So it's a light to frequency converter. Then it would show the frequency in here, and it will show the light intensity based on some equation that I give it, some type of a relationship that is sensor specific. So let's see, for example, I know that this type K thermocouple can go all the way more than 1,000 volts, 1,000 degrees Celsius. So I have here a torch, so I'm going to turn the torch on without burning myself. There it is. So here's the torch. Let me zoom into the display, and I will get this guy, heat it up. So if you have your eye on the temperature, 800 degrees, 900 degrees, 1000, 1025. I shouldn't go any higher than that because I'll damage the thermocouple. But you can see that it works really, really nicely, no problems at all. And I can go the other way. I can turn this torch off now before I burn myself. Here we go. I can also cool it down to really, really low temperatures and see what happens. So I have some liquid nitrogen, and I will do that now. Let me get that prepared. Okay, here we go. I have a little container here. I'm going to pour some liquid nitrogen in here. Now, if you're dealing with liquid nitrogen, remember you cannot just pour it into any container because the thermal shock may shatter it. So I'm going to pour a little bit in here. There we go. So the reason I'm doing this is because liquid nitrogen is at about minus 200 degrees Celsius, approximately. Now a type K thermocouple cannot go that low in temperature. It is not designed, it's out of its specification. So what I'm going to do is I'm going to dip the thermocouple in here like so, and then we're going to look at the temperature on the multimeter here. And because the multimeter knows the characteristic of a type K thermocouple, it should tell me that this is out of range, that it will not be able to measure it all the way down to its actual temperature. So here you go. So right now the thermocouple is in my hand. If I see, if I hold, it's about 30 degrees Celsius. So now I will put it inside. So here's the liquid nitrogen container. I'm going to put it inside there. Here we go. Minus 50, 90, 149, and overload. So this is one of the advantages of having the functionality built into the meter, because it knows that this is a type of thermocouple that is not able to measure. So right now it's still too cold, and there you go. It just warmed up. So now as you can see, it's quickly warming up. We can put it back in, and then back to overload. So when it's in liquid nitrogen, it's actually producing minus 6 millivolt. When I was warming it up with a torch, it was in tens up to 100 millivolt of voltage that was coming out. So that's the entire range of the type K thermocouple. So if you have one of these, experiment with different kinds of sensors. There's a lot of cool things you can do. It actually has an application that you can run on the computer that helps you set up sensors, and then you can do complex sensor measurements. So let's move on to its interfaces with the computer. So as I mentioned before, this instrument has a variety of connectivity capabilities, and they support Alexa and Visa and so on. So if you download the free drivers, you can talk to this unit using SCPI, a programming code, which again, all of it is available online. It has a programming guide. So then you can write C or Visual Basic, or you write stuff in Visual Studio. I'm going to do something in MATLAB. If you have instrument control in MATLAB, you can talk to this directly. It has its own built-in web server separately, which you can just, through the browser, change and look at the data. But if you want to do some specific task, or if you want to collect some data over the USB or the Ethernet, you can use the Visa compatible drivers, which you can download for free. Now, one other thing this guy does, which is useful, is that if you have already written some code for a different manufacturer like Agilent or Fluke or Keithley, if you go under utilities and if you go under command, this guy can actually emulate the Agilent or the Fluke behavior. So this will respond to all the SCPI commands that an Agilent multimeter will respond to. So as far as your code is concerned, nothing changes and it will work perfectly. This is very useful if you want to replace an existing multimeter with the Rigol one without having to rewrite a lot of your code. So I'm going to stick with the Rigol command set because I'm writing the code from scratch. So what I wanted to do just as an experiment was to write a quick bit of code in MATLAB to talk to the power supply from Rigol, this one down here, the DP3068A, which I've reviewed before. So I'm going to talk to this guy simultaneously as this one, and what I'm going to do is I'm going to do some destructive diode testing. And by that I mean I have a whole bunch of LEDs in here, so whatever, is just out of curiosity and also to demonstrate the code, I'm going to take a bunch of these red LEDs, which are quite inexpensive, and I'm going to connect them to the voltage source, and I'm going to monitor the voltage and the current through them, and I'm going to ramp up the voltage all the way to 20 volts, and then we get a plot which shows the diode first turned off, and then it goes through the exponential current relationship, and then eventually breaks down and it dies. So I want to do this a couple of times to see, do these things really die all the same way if you put a lot of voltage or a lot of current through them? What happens when they are about to die? What happens to the current characteristic, and so on? So we'll kind of destroy a couple of these, but we'll do it through code. So one time I'll just show you what happens to the LED as the voltage goes up, and one time I'll show you the instruments automatically ramping up the voltage and measuring, and then finally we'll take a look at the code on the computer. So I'm going to get that ready and I'll show you the circuit. Alright, I have 4 LEDs here which have volunteered to sacrifice their life for the sake of science. 4 different colors, different type of LEDs. So I'm going to put the first LED, the red one, in this rig here. So what is going to happen is that the Rigol power supply will create a voltage, and that voltage will then get in series is connected with the multimeter. And the multimeter is set to measure current in the high mode, so it's displayed right there. And by putting the LED in the middle, I'm able to measure the voltage and the current through the LED. The voltage across the LED is a little bit different than what is actually across the terminals because I have the cables, as well as the internal resistance of the multimeter when measuring current. But it's pretty close because I'm on the 10 amp setting on the multimeter, so the resistance is quite small. So what I'm going to do is I'm going to go on across and I'm going to start the code. And when the code is started, you will see the voltage turn on and continue to rise up. So let me start that. Here we go. So the instrument is now doing, the code is now running, and you can see the power supply has already started to go up. So it's at 0.8 volts, 1.1 volt, and so on. And there is the current. The diode hasn't turned on yet, so there is no current. Here we go. Diode just turned on, 9 milliamp, 14 milliamp, 20 milliamp. So now the current is going up. It's getting brighter and brighter and brighter. Now it's burning 60 milliamps, way over the intended range. 85 milliamps now. 90, 100 milliamp. Uh-oh. 117 milliamp. Oh, this is a tough diode. 131 milliamp. It's getting dimmer now. 140 is already at 4.8 volts. 150 milliamp. Doesn't seem to be climbing as fast anymore. The computer is plotting the current versus voltage. Oh, then now it's kind of becoming an orange color. It's taking 170 milliamp right now. So if we go back here, you can see 172 milliamp. It's going up. The voltage is going to continue to go up. It's set to go all the way to 20 volts. I'm wearing goggles because the LEDs can explode when they become really, really hot. Oh, it's smoking. It's starting to smoke. And now it's taking, okay, the current is going back down, 150 milliamp, 149 milliamp. It's at 9.7 volts. I'm very curious to see the curve after this sweep is done. Again, do not do this at home because, because you can hurt yourself and you're damaging the components for no reason. But this is for the sake of science. So here, now the voltage is going to continue to go up, 12 volts. 12.2 volts, but now the current has basically dropped down to 0. So the diode is now an open circuit. It completely burned down. So what I'm going to do is I'm going to let it run all the way to 20 volts, and then I'm going to replace the diode with another one, and we're going to do this a couple of times, and I'll show you the plot being generated as the last step. So it's going to run and I'm going to change the LED. Okay, so the red LED is done. Let's try the blue one. Here we go. It's running again, 0.2 volts, 0.4 volts. Again, there is no current at the beginning because the LED hasn't turned on yet, as you can see. This LED will turn on at around 3 volts or so, or 2.5 volts. So while it's going up, let me focus here. So there you go, it's running at 2 volts. So let me focus on the LED. There we go, it's turning on. Oh, this guy is really bright. Now it's taking 20 milliamp, 30 milliamp, 50 milliamp, 86 milliamp, really bright, 130, 150, 170. It's dimming up, became much dimmer now at 156 milliamps, still taking current. It's now flickering. Oh, it actually, there was a glow, orange glow, which I think was when the semiconductor connections actually melted. So now it died at 6 volts. It didn't last as long as the red one, but it was significantly brighter. So again, I'm going to let it run through through the entire 20 volts just to be consistent, and then we'll try the next one. Okay, so for this experiment, the yellow LED is on. So now I'm going to run the code this time so you can see how the plotting happens. So here my code is broken into several segments. It's very straightforward. In this section, it runs through a loop that sets the voltages and measures the current. So I'm going to run this portion of the code like so. And here we go. So now the code, and make sure that you can see that. There it is. So now it's measuring a current versus voltage. So this is voltage, so it's now at 1.4 volts, and this is current. Right now it's a milliamp. There you go, the LED just turned on. So the exponential function is going up higher and higher. Right now it's a 60 milliamp, 70 milliamp, 80 milliamp. The current is continuing to go. The yellow LED is now at the point of, it's now completely orange. And the current is going up. Wow, now 100, 200 milliamp. Oh, it's flattening out. I think the LED is finally giving up. You can see the curve is continuing on. The current started to go back up again. 233, very steady. The LED is now very dim, and the current, you can see, is about to drop. Let's see if it completely collapses. Oh, that's interesting. Some dip in the curve there. I think it's just the LED, that the core of the LED, where the semiconductor and the aluminum plate is all molten. So you can have connection disconnections as the temperature changes. So the current is still at 120 milliamps. Now, okay, it's not dropping. So I believe that was it. Now it's still taking 70 milliamp or so. So, well, it's going to continue going. Let's see if we can keep that up. How much longer? It's now at 10 volts and at 82 milliamps. So now it's more of an interesting, actually, connection is happening, because the voltage is going up but the current is staying constant. And it has these dips, and I think as the temperature goes up, there's a equilibrium between temperature, voltage, and current that it has reached. So now it is still continuing doing strange. There is no light anymore. It's now purely, there we go, and it just died. So at 12 volts or so, at 13 volts, it finally gave up. But we will plot all of the LEDs responses on top of each other to see how they failed and how they, at what point the usable range, they all behave quite similarly. So this is going to continue going on until it's at 20 volts. So I will stop the recording, put the last LED in there, run that test again, and then we'll see the result on top of each other. So here I've compiled the result of all 3 tests simultaneously. So they're color coded with the color of the LED. And you can see that the voltage starts from 0 volts at the bottom left here, and it goes all the way to 20 volts. And if you look at the very beginning, all 3 LEDs behave the same way, where they are designed to operate in this region. At low currents, at low voltages, the diode is not turned on, so there's 0 current, and then the current exponentially goes up as the turn-on junction voltage is reached. So the blue LED turns on the least of the highest voltage required to turn it on, and the other blue, green, and orange LEDs turn on earlier, about 1.7 volts. The blue LED needs more than 2.5, and then the current exponentially goes up. So this is roughly up to about 20 milliamps is the design, the region of operation. Any more than that, you're risking damaging the LED. And then if you continue to go and you don't care about that, you can see all of them shoot up to about 200 milliamps or so before failure happens. So once you reach this area above 100 milliamp, the diode is damaged irreversibly anyway. Even if you turn the current back off, it will never be as bright as it used to be. And they go up, and then they kind of do some funny things here when they're failing, and then they collapse and then they become an open circuit again. Except for this blue one, which had, if you remember during the video, it turned orange in the middle. That's when they actually melted on the inside of the LED. So it shot up all the way up to 800 milliamps at about 6 volts or so. So by using the software and the ease of connectivity to the multimeter and the power supplies and all of the Rigol equipment, you can quickly do different measurements and put them on top of each other in MATLAB and get a quick idea of what you're doing. This was a destructive LED testing, but you can imagine very complex different kinds of sensors and different types of plots can be generated using this language. Well, I hope you enjoyed the review of the Rigol DM3068. As you can see, it's fully packed with a lot of functions, a lot of capabilities, and I suggest that you go onto Rigol's website and just download a data sheet of the unit itself. You don't have to read through the entire manual, but you can quickly get an idea of what the limitations are and what the edge of the measurement accuracy is, so you can make an informed decision. I've been using this free unit for quite some time. I typically don't review anything that I haven't at least used for some time and put it through some stress tests and make sure that it is really good. I'm very, very happy with the Rigol instrument. Most of the time I use this instead of the Digital multimeters that I have on my desk. So go to their website, give it a try, download some of their software and see what else they have to offer. And I only scratched the surface. There's a lot of other tests, of course, that you can do. But this is just the first of the many reviews, Rigol equipment reviews that I have. One other thing that I want to point out is that Rigol has a really good customer support center here in the United States that you can call up, you can talk to them, you can talk to their engineers. I'll put some information on the website when this post goes up so you can know who you can call and talk to. They're very knowledgeable and they are willing to listen to the customers in order to change a firmware or fix a problem that you may find. So if there is a little issue with it, they will definitely fix it, and I've already been talking to them back and forth, and they've been very good at addressing any problem that I have found. And if there is one way you want to kind of support the website, if you are deciding to buy something like this, just let them know that you saw the review on the signal path and that you saw the videos and that you liked it. That will always be beneficial for us to keep a good relationship with Rigol Incorporated. So until next time, I have some exciting videos planned out, just a little busy to get them all done, but there's some interesting stuff coming up in the future, so check back soon.